very much, Craig. Look, I'll now introduce Richard Cass. Look, it's a great pleasure to have Richard here because he's been responsible for several of the tall buildings in Brisbane. The last time he presented for ASCE, he wore all black. He's from New Zealand, as you probably guessed, but I told him he could present again if he toned the clothing down. I'm not glad to see that he's changed his pants, but thanks very much.
Thanks, Stuart. Well, thanks for turning up. I'll reiterate a few points that Craig's made too on trends. Is that we've actually got in Sydney a couple of buildings that are going on the back of the success of the Central Park. So we've got another one for Bullberger with a heliostat, and we've also got another project for PTW putting more plants on the vertical sides of the building. So definitely is a trend that we're feeling as well. And one extra trend, which I'll touch on later on, which I think's sort of coming on, it's a bit of a disturbing one, is in the last 5 years we've noticed the complexity of buildings coming in. You know, before, stuff that we wouldn't even entertain is becoming rather routine, even in that very short space of time. And I'll go through a few, my own personal opinion of why it's gone that way. Now let's see. Right, so what I'm going to cover. So we'll go through a few projects specific to Brisbane. So I've tailored a few projects that we've got under construction and a few that are built. This is going to be a bit of a whirlwind tour just through the basic design concepts that are unique to tall buildings. We'll go through and then the design elements that are also unique to tall buildings that we use to cope with those concepts. Then sort of my hook on this is more about testing and verification that we do because we can for tall buildings. We don't get that opportunity for short buildings, and then how we've fed that back into our modelling and analysis, and so we're getting better designs as a result of that. So let's make a start. I've ripped this off of skyscraper.com. I don't know who did the image, but it's a great one for our purposes because it's got all our buildings in there. So you'll see Soleil and Infinity are two of the Meriton towers that you'll be familiar with. They're already existing. We've got the cluster going on the old courthouse site there. We've got 3 towers going up there, the hotel office and a resi tower. And of course we've got over on the Mary Street and between Margaret and Mary Street, we've got 2 towers there that are under construction. Now where these are is Soleil Tower, that's the end of Adelaide Street. So, and Infinity Tower, these two are the Meriton towers already built on Herschel Street. Sky Tower, been going for about 10 years now and we're up to about level 20. That's between Mary Street and Margaret Street, and that's the 300 George Street site with 3 towers going up there. Just a little quick overview of each tower. So Soleil Tower was our first landmark one in Brisbane. And what's notable about it, it's skinny. It's a very slender building, obviously not in today's type, but still probably stands to be one of the most slender in Australia at aspect ratio of 12.8 to 1. And the other thing is because it's tall and skinny because it's on a small site. And the other thing too is to cope with that, so you've got somewhere to park your car. It's also got a very deep basement. So this basement goes down a long way, essentially about 10 floors. And we're into super hard rock by the time we get down there. So we had massive challenges. In fact, it was proposed as an 11-storey basement and couldn't get the last 2 in there, and so ended up filling it back up and putting some car parking in the tower. Next one was Infinity Tower. Notable about that one, it's a little taller, but it's not as slender. It's not a real slender building, but it's got an extremely light conventional outriggered core. So it's got discrete outrigger sets up it, and it works hard. It's very efficient. So not particularly remarkable in any specific sense, but it is a very efficient building. This would be the recipe I would recommend to a developer, because you're gonna have a reliable, efficient, cheap to build, and it's going to perform well, and it does. Sky Tower, that one's got quite a long history behind it because it started out 10 years ago with another Grocon. We're doing it for another developer, and that one went bust. Had the Brisbane floods, turned into a big duck pond for a couple of years. Bill Berger took it on, and it's been through a few redesigns. this will be probably what it was looking at. It was actually designed for 300 metres, so it's actually got it's a big building, and it's got a pretty chunky core to cope with 300 metres. With the intent is to try and get rid of the added damping in this, because the penthouse space is valuable, and of course they didn't get their ceiling height, so this has dropped back down to 274 metres, so the structure is pretty generous for a 274 metre building. There's a little snapshot of Sky Tower. It's racing ahead. They're on a 5-day cycle at the moment, so building a floor every 5 days, pushing for a 4-day cycle, so it's actually already at about level 18. So that's just showing the first few podiums. It's already got an 8-storey basement under that lot. 300 George Street. This one, you'll see that starting to move along as well. What we've got here is 3 towers. There's a resi tower, conventional RC core, discrete outriggers, 270 RL 274, around about 270 metres above ground. So we've got conventional RC and discrete outriggers, PT floors, of course. The hotel is the shorter of those 3. That one is a precast arrangement with a sort of fairly complex, messy core. I'll talk about complex buildings. And the other one's a commercial tower. It's a steel framed one, so it's got a concrete core, but steel framed floors, metal deck. And so it's moved ahead quite a bit further than that now too. And there's another one, Mary Street. This is on the back end of the Sky Tower site. It's a it was actually initially proposed as a D-shaped side core commercial tower with a column grid of around about 12.8 by 12 metres. So conventional sort of commercial tower grid. The demand's gone, so it's a hotel now. About an 8-metre grid suits the hotel better. So it's got a massive transfer slab. And it's been changed from a commercial to a resi, and it's got every red flag of a complex building that you could imagine, and we'll cover that later. Now, not specifically a tall building, but I thought I'd throw this up just to show off a bit. This is one we've got going in Sydney, and it's not that tall a building, but it does have a lot of the inherent traits of a tall building that we have to deal with, problems we should have to deal with tall. Essentially differential shortening, because this thing cantilevers 35 metres sideways. Okay, so they're effectively like 10 stories sideways, right? So commercial tower, and you can see it's sandwiched between 2 freeways. You can see the 2 freeways coming this way, and it's cantilevering over another one that passes underneath there. So that one's they're just demolishing the old IMAX theatre at the moment, and this is going up. Right, so I'm going to cover some tall building concepts. Just, I'm not going to assume everybody knows everything about your basic things. So we've got wind forces. We're going to cover how we can modify the wind forces on the building. So that leads on to the building shape and how we tweak the building shape. I'm just going to touch on these things because this is really Leighton's court, and he can correct my errors on this. Then we'll cover sway accelerations. Again, I'm just going to touch on the principles, so you can, because we're going to lead on from there to design elements, right? And then the next thing is axial shortening, and then sequential construction. Now, one thing about tall buildings, just in general concept, is that there's a number of these principles that these concepts, if you like, I'm going to cover, are unique to tall buildings. Typically 150 metres and tall. Obviously, if you're very slender, shorter buildings count as well. But we're talking typically of buildings about 150 metres above. We just don't have a lot of these concepts like I'm going to talk about, like vortex shedding and detailing of buildings and the actual shape of the envelope and all this sort of stuff, actually being that relevant to a building unless it's above a certain height. So these things kick in at about 150 metres. You really don't get these problems. Now, what you get with a tall building is we're far more interested in how it moves, and more so as it gets taller than how strong it is. Okay, obviously both matter, but when you're designing a small building, you do a very simple linear model, and you get your answers out of it, and you design to those strengths. That's pretty much the end of the story. Whereas this, we're interested in how it moves. Specifically, what we're talking about lateral accelerations, and we're talking about differential shortening. So those are the 2 biggies, and so this is where we lead on. So we're going to cover building shape and detailing, which is to manage the wind forces, so we can change those. We get into vortex shedding. I'll just touch on that. That's Leighton's court. Sway accelerations. Again, it's pretty much more of the same. And then damping, you have a certain amount of inherent damping. I'll explain what that means and talk about added damping. And so that leads on to our solutions of how we fix these issues. All right, so first concept, wind forces. We can't change the wind speed, but we can certainly change the forces that wind puts on the building. Right, now how we do that, we'll cover in this next slide. Okay, so what matters is plan shape, steps and variations to the plan, vertical tapers, notches, and you'll see with these two buildings here aren't just that shape because that's what the architect decided was pretty. These two are highly tuned as a result of iterations that have gone into wind tunnels. So a lot of stuff which you might just think, oh, that looks quite nice, or might have some other reason, are actually being the result of several iterations of study, particularly the Burj. So if you have a look, you'll see that it's got 3 buttress corners to it, and you'll see they're stepped all the way up the building. And you'll also see it tapers. You'll see that the floor plans are all different as it goes up. They actually move around as you go up. If you have a look at Taipei 101, you'll see notch corners on it. You'll see the necking, the change of plan shape. Now, all of these things, they all do the same thing. They all mess with the vortices that come off the building, okay? So the last thing you want is for the vortices to be in a regular pattern. So every one of these does the same principle of trying to mess with vortice patterns. So, we have some general rules of thumb, but we really don't know how these things work or how effective they are until we put them in a wind tunnel. And a little simple thing like those notches in the corners there, Leighton will tell you how much difference it actually makes, but I understand it's anywhere from 10 to 25% reduction on force on the building just by a detailing measure. Okay, so first measure, we play around with the shape of the building. Vortex shedding, again, I'm just going to touch on it. I've got here an analogy of a river. Right? Now you can see the rocks there. They are analogous to the building, and you can see behind, you can see the eddies that form behind the rocks. And if you watch them in the river, you'll see them wind on downstream. One forms on this side, and you can just watch it wind down downstream. You'll see one another. It's very obvious when you look at a river, and it's exactly what we get when we look at the vortices that, we can't actually see them in the air, of course, but this is what happens in the air. And Leighton will give you more on that, I'm sure. So it's a little bit more of the same. This is really just one thing that might surprise you if you haven't been introduced to these concepts is that the wind, if you've got a rectangular building and you've got the wind blowing on its bluff side, tends to be the less critical wind direction. And the reason is because when the wind blows along the direction, you get your biggest response crosswind. So with the wind blowing this way across the object, you get a response in the perpendicular direction. I think Leighton will cover that in more detail as well as to why that happens. Just to show we're serious, this one here, the Tacoma Narrows Bridge, it's a pretty well-known slide, and there's a very good video footage of it if you ever want to watch it. And if for any yachties here, if you have a look at the water there, there's barely any white caps on it, so it's probably less than a 20-knot day, yet it was enough to collapse a bridge. And the concept working there is vortex shedding. Right, and so now how this concept of vortex shedding and how it interacts with the building and makes it sway around, why does it all matter? The driving force is going to be the sway accelerations. So we're interested in how the building responds. Now, just to give you a bit of a handle on it, now these are root mean square values, I understand, but just to give you an idea of what they mean, is that gravity is 1,000 millig's as a yardstick, and our ISO standards for accelerations in the building are around about 5. Okay, if we're building an office building, we probably go to about double that. And what that and why are we concerned about this is that it comes down. It's a serviceability issue. It comes down to occupant feeling of safety and maybe feeling nauseous, and it's very subjective. Some people will feel it, some people may not. Okay, so for a residential building, we're up around 5. Probably double that for an office building because you're not so inclined to be lying down. I'll give you an example. This is Soleil Tower, and without any we get an inherent damping, and I'll cover a little bit more about what damping means, but there's an inherent damping in a building, so we just assume for service things are at about 1%. And so if you have a look at that, you'll see without any added damping, Soleil Tower here in Brisbane has a will be subject to accelerations of around about 6.4 milli-Gs, right? And our target is down the bottom there of about 4.5. So to get to that figure, we looked at a few options of adding damping, 0.5% and so on all the way up, until we found 2.5% was our optimum amount of damping. And so we damp out the we actually damp out the second mode in this one because it was more convenient to put the tanks in those directions. But so you can sort of see that 1.5 extra added damping onto the one gives us 2.5%. And so there was our targets. We met our target. You can see where we started, and you can see we were trying to meet the ISO standards. So that's your first concept of movements that we're concerned about. They start to drive the form and structure of the building. So we've already covered the detailing and the shape and the form of the building, modifies the wind forces, and then so once we've got those wind forces down to something that we can, as low as we can get, and so then we have to deal with the lateral accelerations. The second movement we're interested in is axial shortening, or more specifically, differential shortening. So if the whole building shortens by, a metre, nobody cares. But if we shorten one bit by 0.5 metre and the other bit by 1 metre, now we have a problem. So it's the differentials that we're interested in here. So what we do is we look at axial shortening is broken up into basically 3 components. So we have, there's just drying shrinkage, it's a significant part of it. We've got elastic shortening, so that's the bit that'll spring back up again if you took the load off it. And then you've got creep shortening, that's the bit that won't spring back up if you, after you put some load on it. So creep matters on early age concrete strengths, okay, so it'll squish down, doesn't come back again. Now, to try and manage those ones there, we end up with the interaction of those 3 there is you get this classic curve shape. Now, if anybody's good at reading graphs, you can see that it actually curves back on top of itself and doesn't seem to make a lot of sense because you've got the top of the building shortening more than halfway down. Okay, and so to make sense of why that's going on, and the reason is we build level floors. So as the building goes up, so the floors typically, I should have mentioned that as well. Columns are more highly stressed than the core, so say it's all RC construction, the columns tend to go down more than the core does, so you end up with floors sloping like this. So as you go up, as you build up, so your floors start to droop as you go up, right? Now, but of course we're always pouring levels floors, so we call that slab compensation because we're compensating for the droop. So although the columns have already shrunk a little bit, we pour a level floor. So the last floor that goes on is level, and so hence that's taken into account with this characteristic curve shape. So if you're ever doing creep shortening calcs and you don't end up with a curve like that, you've probably done something wrong. Now, here's a little example with this. Another concept is stress matching. So we have a number of tools to try and deal with axial shortening, which I'll get into. But just for scheming things, stress matching is one tool that we use. Now you'll see on the side there's 2 columns, and one you can see it's quite a big trib area of floor, and the other one's got a very small area of floor, yet they're the same size column. The reason is it's the proximity to the core. So the one over on the far side has a greater appetite for being able to shorten than the other one. And the reason for that is just if they both went down, for example, say 50 mils, the one on the outside, you might live with that because that's over a decent distance. The close one would be certainly unacceptable. A couple of other factors about that one. You can see the big columns, they're mega columns. They're part of the outrigger system and they're oversized for gravity. So they tend to have very low shortening, which gives us, it sort of compounds the problems, if you like, because you've got these big, big mega columns that aren't very highly stressed under everyday conditions. Right, so as I was mentioning, we've got the most extreme column way away from the core. It's got and it can handle quite a bit of axial shortening, whereas there's one only not too far away, about where are we? I think. Thought I had a distance on there somewhere. Yeah, we go 4.5 meters. So it's only around about 4 meters from the core. So that can't handle much shortening. So to manage that, we can stress match it. So we make the columns a little bit bigger, so the stress under them is more closely aligned with the core, and so that's one technique we can overcome axial shortening. The second one we can do is we can outrigger. So if we clamped onto the core, that's another way of managing differential shortening. And a third method we've got is preset, and you'll see that in here. Where's my presets? Okay, so you can see the presets there. We've got anything from 0 millimeters to 30 mils of preset. Now what that means is that we actually build the floors like that, okay, going away from the core. And so the idea is that when you get to the end of construction, they've come down somewhere close to level. In fact, there's also long term to consider as well. So we normally want them sitting a little high, so at the end of say 30 years when they've stopped moving, or most of the majority's gone, then we pick an average point between those two. So we might start up here, we go there at the end of construction, and we maybe go there at the end of 30 years. You'd be interested to see this. These are actual shortenings. We measure them, and we calculate these first, and then we actually measure them, and this is sort of like the overall shortening. So the building's shortening, 90 millimeters over its height. So it's got quite a bit of scope for differentials if one bit was only 90, another bit was 50, for example. Right, so now sequential construction is another thing you need to take into account with axial shortening. What we end up with is, when we look at creep shortening, there's a number of factors we've got to take into account. Now, if you're designing just a short building, say 25 floors or something like that, and it doesn't have any outriggers, what we do is we do a linear model, and we assume it's built instantaneous. Okay, so it's just like built in got 1 second, and all the stresses that are there is what we've got. If you try doing that for a tall building, your answer will be completely wrong. Not a little bit wrong, a long way wrong. And to illustrate what sequential construction is and how it matters, the roof outrigger is a brilliant way of explaining it. So if you have a look on the left there, if you come up with your outrigger building, and I put a roof outrigger on for a very specific reason here, and you do an instantaneous analysis, what happens is the columns are higher stressed than the core, so they'll shorten more. Elastic, creep, they'll go down more, right? Now, as they shorten, they'll haul down on the outriggers, and you can see the outriggers are bent down there, and so the outriggers are under a lot of stress, the columns are under tension, and the core's collecting some of that force, and it's got more compression in it. Is it real? Of course not. So, because what happens is when you build the building, so there we go, we built the columns and built the core, and we're right at the top, and we're at the top floor about to build the outrigger. There's no stress at the top of the column, there's no stress at the top of the core, and then we go and build an outrigger set on top. So what's the stress in the core on the column? Well, it's close to 0. But this one over here would tell us that there's a lot of tension in the column, probably about 3 MPa sitting in that outrigger set at the top of shear. So that's the concept. That's why we do it. So sequential construction is you have to put in, you run the model for say 2 floors. It analyzes all the stresses in there. It remembers what the stresses is. Then you run another floor and you modify all your properties. So for instance, like this level here has got say 7-day-old concrete, so it's got a representative modulus. And this bit down, the next floor below has got 14-day-old concrete, so it's got a representative modulus, and so on. And so this is just sequential construction. You run a sequential construction model to represent those sorts of factors. Just to sort of represent what goes into your sequential is that I talked about linear elastic. That's just the thing will just, if you took the weight off, it would spring back up again. You've got creep. That's the bit where it sort of starts to relax, but it stays there if you took the load off. So that's the second one. The sequential basically corrects all of this stuff. Your floor preset, we'll throw that in as well because we're trying to. That's another part of the mix. And then of course at the end of construction we've got a long-term part. So all of these sort of things are taken nicely encompassed into one analysis. This used to be enormously complex to do, right? We used to run multiple copies of models, all stripped down to different levels. Now we've got time-dependent material, time-dependent variable material properties, and so it does it all in one big package, and it is starting to lead towards people thinking that complex buildings are okay. We'll get into that in a second. All right, now, so there's your basic principles. Layton will cover a little bit more on the specifics of actually wind vortice shedding and all that sort of stuff. And now we're going to talk about how we cope with all these problems. and what we do. Now, our basic toolkit for a tall building is going to be the outriggers sets. Okay, so we'll talk about outriggers, mega columns. We talk about belt trusses, which is essentially an extension of outrigger systems, and we talk about damping, inherent damping, and added damping. First of all, what an outrigger is, I've updated my woman on skis, and so on the right here is a section of Infinity Tower, and you can see it's got discrete outrigger sets. The top one's basically is a damper tank outrigger. Sorry, it's an extension of the damper tank. Doesn't do an awful lot in terms of an outrigger. These two main ones are working, and so the little bits that connect the core and the columns, they're the outriggers. Now, to what they do, my analogy is the skier over here. So her body is the same as the core of the tower. Her ski poles are the columns, and her arms, of course, are the outriggers. And so, of course, if I'm standing here in my skis, I'm not very stable. Ski poles, I'm stable and I'm stiff. Okay, so it gives the strength, and it gives the tower strength, and it gives the tower stiffness. And so it's attending to two things. It's attending to both strength, and it's going to attend to our service conditions of sway accelerations. And it has another benefit as well, is that by clamping the columns onto the core at intervals, we manage differential shortening as well. They can't shorten because they're clamped onto the column by the outriggers. The downside is that we get massive forces in outriggers. They're always very hard to design because of these massive forces that are involved. Here's a little snapshot of some, it's an analysis model, of course, but it shows up nicely in yellow what the outriggers are. And you can see this is the Infinity Tower core in 3D, and you can see there's two gravity columns, but otherwise all the other columns are joined on with outriggers. And so that remaining column obviously had a bit of preset on the floor to manage it. A few other outrigger configurations. That one there is George Street Resi Tower on the left. The one on the right there is the commercial tower. We've actually found, because the commercial towers can handle bigger accelerations, after we ran that through the wind tunnel, we were able to actually ditch one of those outriggers on there. But you can see they've both got various forms of outrigger configurations. I like the little snapshot because it gives you the difference between a lateral stability system, which is the red bit, and the yellow bit is all the gravity ones. And why I've shown you that is because this snap here, which is the same thing again virtually, as you can see in there, is that there is, I don't know if I can use the pointer. These bits in here, they are internal, what I've named internal outriggers. And the reason is, as you can see, the orange bit in the middle is the internal core and it's not connected to the outer bit. Now, you can imagine the differential shortening issues we're going to get there, right? Just as we've covered. So the middle core, it's got very little floor around it, so it's going to be quite lowly stressed in axial force, as opposed to the core, which is picking up the outer core, which is going to pick up a lot. So to manage that, we did a twofold thing. One, we went through the stress matching procedure where we skinnied those walls up to they're stupidly thin, and the other one is we put these little internal outriggers. Okay, so the stress matching reduces the forces that we have to manage, and the bit we have to deal with is that. Now, why it matters is because that internal core, you can see, is probably only about 2 meters away from the outer core. So we've got very little tolerance. If you had more than about 15 mils across the floor, you'd notice it. As I said before, they're horrendous things to design. I'm yet to see one that works well, works comfortably, I should say, or is easy to detail. They're always hard to detail, and this is the sort of congestion issues you end up with. Those are 40 diameter bars there. And you can see the big anchor plates, so that's another thing too, trying to anchor these things. Now, as a little extension of outriggers, I'll just introduce you to belt trusses. So the pink bit across the back, although it's a solid wall, is effectively a belt truss. And what they do is they engage a bit more gravity of the building, so some gravity columns. They engage it with the lateral system. So gravity is our friend as far as talking about lateral stability. The more gravity we can do, the less RIO we put into the building. So they could be outriggers from each of those columns back to the core and would do exactly the same job. So all we're doing is just belt trusses enable you to engage gravity columns with the lateral system. Now, on the left there, you'll see these are actually pure belt trusses with no outriggers, no outriggers as walls as such between the core and the columns. And we call those virtual outriggers. And they've got good characteristics as far as creep shortening. It gets rid of all those overstress problems you have with creep shortening between the two. How they work, we don't have time to go through in depth of explaining it, but the floor, and essentially how it works is that the floors above and below the belt truss going around the perimeter act as the push and pull, and so the diaphragms have become an integral part of it. So in theory, like an outrigger like that would probably work without the floor diaphragm. Well, that one probably wouldn't work very well, but typically they would work without the floor diaphragms. That one there, the floor diaphragms become a very integral part of it, because the fact that if you start to rock it over, you get a push-pull between the floor plates. You're trying to share the two floor plates. So that's a virtual truss. Good to know that they exist. We find that in Brisbane we never got one to work satisfactorily because your wind speed's up around 60 metres per second, but we definitely get that building was proposed for Sydney at about 300 metres tall. They definitely work down there because the wind speeds are much lower. At about, yeah. Right, the next thing I'm going to touch on is damping. Damping is basically, if you imagine, if you push a swing, it eventually stops swinging, and it's the inherent damping that stops it swinging. Building's the same. You give it an initiation, it'll eventually fade out. That's your inherent damping. And we can add some damping to improve that. So if you keep pushing the building, right, you can exaggerate the swing, and so you need, and if you don't have enough inherent damping and you get very little when you get tall, we can add some damping. So we've got a number of elements in here. Dashpot dampers, and sort of like what you find on your bike or on your mountain bike or on your car. So not very common, but so there's a mechanical damper. Doesn't need to be tuned to the building. Then we go to tuned mass dampers. Now how they work is they represent a percentage of the mass of the building. So as I was talking about before, if you put like 1% damping in, you take the modal mass of the building, and in rough terms, if you took about 1% of that weight, what happens is when the building sways this is hanging on a pendulum and it's tuned to the same frequency. So if the building's swaying like this at say 7-second period, and you've got this tuned at 7-second period, they'll counteract each other, right? And then you just need to damp that out, and that's your tuned mass damper. This is in the Taipei 101 tower. You can see that big ball of steel sitting in there, and that's essentially how it works. The building sways one way, and this sort of counteracts. And remember, only damping out just a small percentage of the whole building mass of the building. These are now it's a similar sort of concept, but this is a slosh damper, and this is what we've got in Soleil tower. And you can see they're U-shaped tubes, right? Now, how they work is very similar. We tune it so that the water sloshes back and forth inside the tank at the same period that the building sways in the direction that that tank's aligned. Okay, so that's how they're orientated on the Soleil tower, and that's what they look like. And you can imagine, so they're quite big. It's about 7 metres tall. The tube's about 3 metres for the actual tube part of it in each direction, and the water sloshes back and forth. The period of the building is around 7 seconds. The period of that will be about 7 seconds. So slosh back and forth inside that tank. Yeah. Infinity had them as well. We actually double them up as sprinkler tanks, so it's not wasted work. We just had to shape them differently. These ones didn't need to be commissioned because we were right on that borderline of not needing any added damping, so they didn't need to put the damping mechanisms in them. Now, what we do is with tall buildings, because they are service dominated, we need to test for how they're going for that design criteria, and we test it as we're building. So we do we get the wind consultants to do scale model testing, and even that damper tank had a scale model test on it. We get full 1 to 400 scale wind tunnel models usually done. We measure axial shortening as the building goes up, and because remember we talked about sequential construction, we get measurements as we go up from the analysis model. So we can say, oh, level 29, these should have all shortened this much. So we check our predictions as we go up in height, and then we go back to the model, and if it's not correlating, we can make tweaks as we go, so we can predict it as it gets further on. So we measure axial shortening. We do concrete modulus testing, and so that we can go back and calibrate our model as well. So if we normally concrete's coming a little bit stronger than we assumed, so our moduluses will be proportionately higher. This is one that Mel did for the that damper tank on Soleil Tower, and you can see they made a little model, and it's because it's got some funny little cranks on the corners there. It's not an easy thing to predict what the period of that tank would be by pure calculation. Way easier to do a dimensional model. So that's what that was. This one here, Lane will show you lots more pictures of wind tunnel testing. Again, that's Soleil Tower sitting in the wind tunnel. You can see the Story Bridge over there. A bit more stuff. And what we get out of that is they give us some base moments, and so we get a little diagram like that, which looks horrific, but it's actually really useful. And so from that, we can work out where the problem areas are. The envelope of that basically is what we designed to. That just gives us a base moment. Our analysis model, so we're using ETABS or whatever, that gives us the distribution of those forces up the building. Right, now, we played a little game with wind consultants, and I think I've talked to some of you about this before, where they don't tell us what their measurements are until we tell them. And so what this is when we get to about 80% construction, now this matters for, say, added damping, we'll go and put accelerometers, so the wind consultant put accelerometers on top of the building at, say, 90% construction. We strip our model back to represent where that construction's at, and Mel won't tell us what their measurements are until we tell them what our guesses are. So we take our model predictions, and then they tell us and see how close we are, and then what we do then is if we're a bit out, we can tweak our model until we can get those numbers to correlate. Then we build our model back up to full, and then we predict what the final ones will be when we've built that last little 10% of construction. And then, so they'll retest at that stage, and they've got a little bit of tweaking they can do on these tune mass dampers. So if they need to fine tune because all this is about, if we were really wrong, we might have had to redesign the tank, make it a different shape and so on to make it work. And so this last bit, we do a final check, and if we're good to go, we'll be pretty confident that once those tanks are filled, the thing will perform how we expect it to do. What the drop test is, by the way, is they have a crane drop. Now you can just use the wind. The wind will blow the building around, and the accelerometers will tell you what the first mode is, second mode, and third mode. 2 translational modes, 1 torsion mode. But you can't measure inherent damping. And what inherent damping is, so this is where the crane drop comes in. You can drop a bit of a load. You won't even perceive the movement. It might be 1 millimetre, and the tower moves, right? And the tower moves, and it decays. And that decay is the inherent damping. So you can measure that decay. So that's the whole point of the drop test. Otherwise, you just go up there on a windy day, as you can see what the third test is up there. Now, there's our concrete modulus testing. We do test as we go along, and we take those values and we put them back into our model. And axial shortening, we have to obviously go for a remote site, and we measure how the building shortens. Now, all of that data that we've got, as we've measured modulus properties of the concrete. It's got a strong correlation to strength, so we can sort of infer from there. So we've got our material properties, and then we've actually measured the axial shortening as we've gone, and measured that against our sequential construction model, and we've gone and done this. So we've got all this useful data that we've measured our analysis model against, right? So we can go back and see, where errors lie, and we can actually use it a little bit more than that. Is that, for example, what we'll tend to do is I find that we're consistently picking our 2 translational modes as longer periods than we'd actually measure, right? But we find that the torsion tends to be on the other way. And that's not great when we're trying to scale it up. So for instance, like we might sit there with, say, 10% on one side and 10% on, say, 2 translational modes sitting 10% on one side and torsion on the other side. We can't scale it up because we're already sitting 10% accurate each way. So it's that proportional difference that we're very interested in doing. So we go back to our models and we say, oh, look, we've got numbers which are very close, but they're proportionately got error in them. So we go back and we start looking at how we've modelled our headers, because headers would be very responsible for torsion. And then we look at translational modes. So if we're trying to tweak say the torsional mode, we'd probably draw our attention to the headers and see how we'd modelled those and say, did we model them stiff enough or too stiff or whatever. And so we've actually over the years refined our models, and we're getting very, very accurate answers out of the results of our tests now. How accurate do you reckon your average engineer's modelling is? Could I get a show of hands? Who reckons sort of like, I don't know, 90%? Anybody modelling at 90%? Okay, 80%? Anybody reckon 80? 60? Nobody thinks they can model to 60% accuracy. Really? Okay, that's interesting. Because you're probably not far off, to be honest. Right, now I'm going to touch on, I'm running out of time, but I'm just going to touch on structural complexity because it's something that's a trend that's happened. Now, here we've got here is that a very regular building, very hard to screw up. Right? You can put in an experienced engineer and the thing will probably perform well, mainly because its post-elastic behaviour is going to be pretty much like its elastic behaviour. But if you get a complex building, even an experienced engineer is going to be guessing and not that certain, right? And if they are, it's quite revealing in just its fact in itself. Here is a complex building. It's one of ours, and you can see highlighted in red. This building has every red flag in the book. Okay, it has a side core. It even has an offset core. It's got a 2-metre transfer deck swinging around in the air. It's got raking columns, it's got discontinuous diaphragms, it's even got precast walls and things. And so this thing is like, all of the stuff is actually compliant with an Australian code. You can say, yep, and this is a big thing I find is a lot of people using design codes, particularly Australian codes, as design manuals. They are not. They are a means of compliance, all right? So my warning here, my big message of the thing is, stop believing your ETABS models as much as you do, and stop using design codes as design manuals. They are a means of compliance. It's something you tick after you've done a good design. It's a little bit extra. You can see raking columns down in the lower levels. You can see the transfer up at level 8. You can see the offset core, things torsionally eccentric. And how we get this to fly is we actually keep it within an elastic range. We don't push it post-elastic, okay, because I would lose complete confidence in any results. Yet the Australian code would allow you to put ductility 3 on that thing, which would be absolutely ludicrous. Right now, and on the same thing of complexity, is that ETABS models are very seductive. You know, like you look at them, they've got beautiful graphics now. They used to be screeds of numbers. You know, you used to get out literally like 100,000 lines of numbers. I'm not kidding. And we had to sift those out to try and design stuff too, right? Now you've got beautiful graphics and you start to believe them, okay? And the trouble is that the lead engineers tend to be, you know, my age and have got no idea how to investigate an analysis model, and they're basically getting hoodwinked by that bright young PhD graduate that's building the model and have no idea that what they've done is absolute folly. They believe their model, they are probably wrong, okay? So you need to stand back a little bit and take a little less confidence in saying, oh look, it complied with an Australian code, or look, the ETABS model told us that we can, okay? They're rubbish approaches to designing buildings. And I've written that down for you, okay? So this one here, you know, it's torsionally eccentric. The Australian code has got nothing in there about vertical irregularity. It has nothing in there anymore about torsion, right? So it's just like, it's loony if you thought that you could just design to a code and say that's it. Just a few snaps there. All right, so just a quick summary. If you're looking at models, look for loading as your first place you're going to find errors in there. Modal mass is actually another significant one we find has got a lot of error sitting in. This is our feedback of information back into our analysis model, is that we're feeding the stuff back in and we're saying, oh look, we've got a bit of error here, where can we track it down to? And we do get a few little clues, like whether it's a torsional problem or whether it's a translational problem. And we start to say, okay, loading's a biggie, modal mass is another biggie, again trying to define your weight of the building. Boundary conditions, common mistake. I've seen this a lot of times where understand pressure bulbs underneath foundations has a big influence. Stiffness modifiers, another one. You need to understand them, you need to understand its application. Is it a seismic application? Are you pushing your ductility? Or are you in a wind situation where it's much more elastic? Are you testing for a service situation? Are you testing for an ultimate limit state station? These are all the things that influence your choice on stiffness modifiers. This is an art. It's not something where you just go, here's your answers that you follow. There's lots of factors. You don't just say, hey, stiffness modifier 0.6. Not true. Okay, you've got to look at its application and what you're using, you know, where you're going to use it in the building. Meshing. Auto mesh and ETABS is absolutely useless if you're doing a multi-story building. Your model will be a dog. Okay, so you manually mesh. You have to manually mesh, and you have to know how to mesh. Okay, so it's very nice to see Revit models. We can port them into ETABS, and they run. They just about crash every computer that tries to make them work, and they're absolutely useless. We can't get answers or what-if studies out of them. Secondary elements, precast. When I interview staff, we give them a bit of an ETABS test, okay? Because everybody tells me they're an expert at ETABS. And so one of the things I tell them to do, model me a precast wall. You know, the stuff that everybody ignores and puts in as a line load? Okay, that's wrong. And so if you can do that, that's normally our basis for saying you would employ you. Nonlinear effects, post-elastic and ductility assumptions, another sort of hotspot for error. Bottom line, your model has to represent reality, and your base model represents reality. Quite happy to see the conservatives and the engineers love to build into their models. They are sensitivity models, okay? They're not base models. So when you're doing something like, oh, I just wanted to be conservative, no, because the forces went somewhere and they went somewhere else. So we want to know the first pass, we want to know where they went, and so that's always your base model, model's reality. Probably too much to go in. Right, so it's a bit of a summary of what we've gone through. Don't make your buildings too complex, and try and keep it simple.